This is Physics 2212, Lab 6, Magnetic Molasses by Manveer Singh. So introduction, the purpose of this lab is to study magnetic induction and eddy currents by analyzing observational data of a bar magnet that is falling through an aluminum tube and comparing it with computational models. So our observational model is the bar magnet in an aluminum tube, and the computational is through glow script. Some principles used would be Faraday's law, the Biot-Savart law, and Newton's second and third laws. And so our system in this entire situation is the bar magnet and the tube itself, and the surroundings would just be everything else in the room. In a brief preview of our results, the experimental time was 1.15 seconds and computational showed 0.8 seconds for the magnet to fall through the tube. So the principal equations used, we're using Faraday's law, which also incorporates Lenz's law if this was negative here. And then we also have the Biot-Savart law for a moving point charge. And we also have Newton's second and third laws, which is just stating that net force is equal to a change in momentum. So our experimental procedure, if I can play this here, you can just see that basically you get a bar magnet and you drop it through the aluminum tube, and it's supposed to fall slower. So you basically record the time that it takes for the magnet to fall through completely for 5 times, which we did that here, so the video is a bit long. And then you take the average of the 5 times, and we're going to assume that there's negligible air resistance. The bar magnet acts like a magnetic dipole, as you can see here, and that the only forces that are involved are the magnetic force and the gravitational force, which is also shown here. So experimental data, the length of the tube is 0.3 meters, width was 0.006 meters, inner radius is shown here, and outer radius is also shown here. And the properties of the magnet itself, the mass was weighed at 0.029 kilograms, and the dipole moment was calculated to be 4.77 ampere meter squared. And then these are the each time for that we got as we were dropping it for each trial, and then the average time showed 1.154 seconds. So the computation model initial conditions, over here we just have our constants, and over here we put our initial conditions of the tube dimensions, and over here we put the dimensions of the properties of the magnet. And over here is where we are basically calculating the magnetic field of the bar magnet. We put in the different R hat formulas, and then over here is the dipole moment shown as well, right here. And we also have the magnetic field of a dipole shown by this equation here. And then to create the magnetic flux, again, we're just basically inputting this formula, Faraday's law, over here, where we just are calculating, the change in flux. So the forces that we're putting that we modeled again are shown here. We basically said that the magnetic force from the tube on the magnet is 0, but for the ring in the tube it's not. So you had to just basically find the different forces, and then over here is just us translating that into the vector force. And over here is just again calculating the magnetic field at each ring, and we just are adding each ring, that's our n. Our n value is the amount of rings that there are, and then we calculate the net force by adding both the gravitational and magnetic together, and then you can do velocity and position update formulas by rearranging the equation there. So computation model results in visualization. You can see over here a graph is shown where the time in the tube is shown about to be 0.8 seconds. And you can see over here that the gravitational force equals the magnetic force during this horizontal part. So then interpreting the simulation, the red down here is counterclockwise, blue is clockwise, which was found using Lenz's law. What happened when you flip the magnet? The magnet would still fall the same, but the current directions would be flipped as well. And then how does real world amount of time compare to the computational model? Computational is shorter, possibly due to not accounting for air resistance or human errors in the timing. And then what does the plot shape tell us about the forces? Basically, the gravitational force is always greater than the magnetic when you are entering or exiting the tube, but equal within. So basically, over here, we're saying that gravitational is greater, and here as well, but over here, they are equal. So errors and assumptions, again, we assume the air resistance is negligible. The bar magnet is acting as a magnetic dipole, and only gravitational force and magnetic force exists. Error, again, there could be timing not precise. We could have found an inaccurate magnetic dipole moment, and then the friction from the magnet hitting the sides of the tube and slowing the magnet down could also have been a factor. And again, air resistance was not accounted for. What if the resistivity of the conductor were reduced as close as possible to 0? Basically, using Ohm's law, V equals IR, decreasing resistance would increase the induced current I over here. and this would produce a stronger opposing magnetic field, which would then slow the magnet down more. And then what if we had holes in the tube? Basically, this would decrease the overall current in the tube, and this would just, in result, produce a weaker opposing magnetic field, which would cause the magnet to fall faster. So in conclusion, Faraday's law explains how magnetic forces can cause induced currents. By studying these forces, we can understand this natural phenomena. We can also model this computationally, and applying this experiment to real-world scenarios allowed us to see more practical applications of Faraday's law.